Hello, everybody. Welcome back. I hope you're having a great day so far. My name is Michael, and I'm going to be teaching myself some Python today, more specifically, data structures and algorithms in Python. And I'm happy that you're here to join me. I am super excited because we just crossed over a good milestone on the channel here, which I thought would come much, much later in the future. And I'm trying to find my AirPods case so I can put these puppies away. Where did they go? Um, I don't want them in my ears while I'm reading. Where did it go? Hold on. Let me get my. Oh, I'm causing a ruckus. There we go. All right, we are back in business. There we go. Oh, I got a blanket here. It's cold. All right. There we go. We're getting settled in here. Pardon me, pardon me. Kerwin says present. Welcome back, Kerwin. You are marked present for today. I appreciate you joining the stream and showing me support today as usual and getting the stream loaded up. You are fantastic. Thank you. Sorry, I'm getting all settled in here. This is annoying. I can't have that behind me. All right. Okay. Let's get my backpack fell over when I stood up. Oh boy, it's starting off rough here, but we're gonna manage. There we go. Hello, General Talks. I appreciate you coming in and saying hello. Good to hear from you. How are you doing today? Happy Friday to you guys. We made it to the weekend here. We're gonna. It's a good day. We live to see another one, right? Gotta love that at least. All right. My dog is chomping on a bone in the background. I think she might be done with it though, so hopefully, if you guys hear that, something's going on with the chair here. Let's fix this. Here we go. Okay, here we go. We are settled in here, finally. Probably should have done this before I started, but it's okay. We're giving that authentic experience. Well, I'm fine. How about you? I'm doing great. It's Friday. I feel like I needed a little break from work. I'm ready to enjoy the weekend here, kicking it off with some Python learning. It's gonna be great. Gonna get a lot done on the project this weekend. Um, so I'm super excited about that. I want to get some features going and get it working. For the most part of like adding and editing items all together. And then we need to do some testing and debugging just in general, because obviously we haven't really given it some thorough tests. So we need to, test things out this weekend. I will say I'm going to try and stream tomorrow morning around maybe like 9 a.m. Oop, I'm dropping frames again. It's dropping frames. Let me know, guys, if it gets really bad and it starts disconnecting. Hey, okay, I think we're back. We're all right. So, um, yeah, so this weekend we're gonna get a lot done. So tomorrow I'm gonna try to hop on maybe around 9 or 10. I'll stream until about maybe 1 or 2 o'clock, and then I'll hop back on maybe later that night for a late night stream. I'm just headed. I got my girlfriend is having a show uh, for her dance studio, so going to her show and it's in a different city. Just gonna drive a little bit tomorrow and go to the show tomorrow afternoon. Let's put that annoying little hair away. There we go. I am in the west coast of America, United States. So it is 7:11 p.m. for me. So we are on opposite ends, my friend. So I thank you so much for joining me here, and it's good to have uh, an acquaintance on a different time zone here. Okay. Nonetheless, we need to get started here. So yesterday we were introduced to this drawing a ruler, and it just kind of demonstrated a physical representation of recursion happening. It was pretty complex, honestly. It was hard to follow, if I'm being honest. We can obviously come back to this and learn more. I'm going to move on. I think binary, just giving more examples of this might help. So let's move on to binary search here and go forward from there. All right, so we are on page 155 of Data Structures and Algorithms in Python. This is a collegiate level, hopefully. I don't know. It's definitely hard, so it feels like it. Textbook regarding data structures and algorithms in Python. Uh, yeah. Okay, binary search. In this section, we describe a classic recursion algorithm known as binary search that is used to efficiently locate a target value within a sorted sequence of n elements. Okay. One of the most important computer algorithms allows us to efficiently locate a desired value in a data set of upwards billions of entries. A sorted sequence, so it is sorted in some way. This is among the most important of computer algorithms, and it is the reason that we so often store data in sorted order. Values in sorted order within an indexable sequence, such as a Python list, the numbers at the top are the indices. Gotcha. When the sequence is unsorted, the standard approach to search for a target value is to use a loop to examine every element until either finding the target or exhausting the data set. This is known as the sequential search algorithm. Okay, so let's get some notes going here. How do I want to do this? We'll go sorted lists. Slash data sets, right? So sorted lists slash data sets. So we have so the sequential search algorithm. Sequential search is looping over a input over every data. Right, so it says loop to examine every element using a loop. So sorry, using a loop to examine every element in a unsorted in a data set, right? Using a loop to examine every element of a data set until either finding the target or exhausting the data. Until either finding the target element or exhausting the data set. Cool. So awesome. Hey, Jaded Room, I appreciate you coming and leaving some messages. I can't see them anymore, but thank you so much for joining. And how's your day going? I appreciate you coming in. General Talk says, "Oh yeah, by the way, have you learned Lumpy and Pandas? I'm currently trying to learn them too, and I have zero idea of how I can use it efficiently. If you've learned, can you share some tips?" That is on my list of things that I definitely need to. This hair is annoying me. Let's get that down. There we go. That's definitely on my list of things I need to, take a peek at. I want to get familiar with those because they're often used in the field for when companies that use Python or things. So they're definitely necessary. So especially in the data analysis field like I'm in and science in general, I need to know those kinds of things. So yeah, we will be taking a stab at those on the channel eventually. I guarantee you. So just give me hold on, and we will get there eventually. I don't know when, but we definitely need to learn those. Kevox, thanks so much for joining. I appreciate you coming in. He says, if you ever need more help, I would suggest watching BroCode's free Python course on YouTube. His Java one is an absolute banger. Awesome. Yeah, I've watched some of BroCode's videos in the past regarding Python and everything. So those are some great resources. Thanks so much for coming in. All right. Um, for those that are new here on the channel, my name is Michael. I'm a graduate of college. I have a Bachelor of Science in Human Biology and a minor in chemistry. I graduated back in 2021 and I got a job right out of college as a formulation chemist for a biotech company, and I've been doing that ever since. I've received some promotions along my way, and I've been enjoying my progression there. But I wanted to further expand my skill set, and I found some instances in my field where I process data a lot. I have to calculate some chemical matrices to predict theoretical concentrations of solutions in bulk and in mass. So it could get pretty complicated to keep everything in order. And so I thought maybe I could learn some computer programming to help make that easier. And that just kind of sparked this whole fire into learning. And I created this channel to document my progress along my way to help maybe other people in a similar situation either seek motivation or gain motivation, or just companionship from peer to peer, or because this can be quite daunting, and it's definitely easier in some people's eyes to do it with a friend. So if that's something that you're interested in, I appreciate you coming in and for joining me today. So right now we are in chapter 4 of data structures and algorithms in Python. We've already read all of Python Crash Course. We took Harvard CS50P, completed all those the final project. We also made our own independent project, the Task Tracker application. I posted a video to my channel yesterday, just a demo. We completed that and wrote the entire program on stream live, just like we read all of these books live on stream, just like I'm doing now with DSA and Python. We are going to eventually get to Python machine learning, and then we eventually get to Fluent Python shortly after that. Not in that exact order, but we will obviously have a lot of material to get through here, but we are cruising along. And we in the first half of my streams after my 9 to 5 job as a chemist, I try to find 2 or 3 hours to stream quite regularly, and then in the first half I like to read and increase my knowledge further in programming in general, and then more with a niche in Python, and then and my back half of my streams in the second half I will dive into my personal projects. And currently, for those that are new here, we are building, like we did before, we built the Task Tracker application. This was built all on stream with everybody. We had a lot of great suggestions from the chat. And if you want to see the demonstration, it's on my channel right now. We did this about, I'd say, 2-3 weeks ago, maybe a month ago, coming up now. And then now we are currently writing the Small Business Manager application, where it will manage inventory items, convert that inventory into for sale items and then convert that inventory or those specific items into sold items, applying different modes to those sold items via like shipping, delivery, and then obviously creating a general script to manage for the user in a CLI interface, for intaking those items, generating expense reports, hopefully down the line creating you know, tax documents, all those type of general business needs for small business owners that they may not know how to write themselves. I currently manage a small business with my girlfriend on the side, and it's challenging, and I do this all by hand with like Excel documents, and I would just love to have one central program to just kind of do it all on the back end, and me just kind of input things and click some buttons. So we have file saving in here. We've been writing all this on stream, and so it's been really great so far. So if you're interested in all of this and this all looks great to you and something that applies, consider following along. We are cruising along and we just crossed 400 subscribers on the channel. Woo! Hurrah! Hurrah! I honestly, this is so mind blowing. Just like like a month ago, I was like at 30 subscribers, and I was just like alone in the stream, almost with like one or two people in and out, and it was fine. I mean, I was learning a lot, and now it's just even better because I get to interact with you guys, and we're friends and uh, peers in this, learning together. So it's just great. We got some chats. Justin, I appreciate you joining. Welcome back. Jose says that's great. Yes, thank you. That's awesome. Angela, thanks so much for coming back. Welcome. How are you doing today? Kevok says that's awesome. Sounds like a complex job, but looks like you have a passion for it. Yeah, it's great. I love I know I love science, and I'm just trying to further expand my knowledge into computer programming. It's always a good idea to push yourself to be better and develop new skills in general. Jacob, thanks so much for joining. I appreciate you coming in today. Welcome to the channel and welcome to the chat. Avinash, welcome back. Hello. Good to hear from you again. Okay, let's get going. Let's keep going here. So we talked about sequential search, where sequential search is typically an unordered list where you would, I guess it could be applied to an ordered list if you needed to search every single one, but what's important here is a sequential search algorithm will loop over every element in the sequence. That's just a property of it. So, yeah. Sorry, running out of breath here. I often forget to breathe. I'm talking so much and yapping. Let me know if I'm yapping too much in the comments. I'm sorry. In the chat. This algorithm runs in O of n time, right? Because it's in linear time because we search every single one of the values. So we have to check each one of them, creating a one-for-one time complexity or linear time. This algorithm runs in O of n time since every element is inspected in the worst case. Gotcha. When the sequence is sorted and indexable, there is a much more efficient algorithm. For intuition, think about how you would accomplish this task by hand. There's much more, when a sequence is sorted and indexable, there's a much more efficient algorithm. For intuition, think about how you would accomplish this task by hand. Right? So if you were searching for a number, you could you could make this easily log of n by just eliminating half of the list if the number you're searching for is either even or odd, right? Just by doing that, you eliminate half the list, thus reducing it in half, thus taking basically a logarithm in that case, right? Because the log base 2 is how many times can you have the input size until you get to the base case of 1, or whatever it is, or the floor. I'm not sure the exact terminology, but I think this is starting to set up for binary search would be a log function in some instance. So that's how we would do it by hand, or think if you already know you need a really high number, right? You already know you're searching for a recently added user or or just a high value. Why even why even start at the beginning of the list? Start at the end of the list, right? Or you have those types of ways to do it, or take half of the list away and start at the greater half, right? All right, we got some comments. Shrouded Data, do you stream every day? So far I have been. I just been really enjoying my time with you guys, honestly, and doing this. It does not feel like a burden. It does not feel stressful. It doesn't feel, um, you know, it's obviously hard, but when you accomplish hard things, you feel good. So this is like kind of going to the gym mentally for me. Um, I really enjoy it, and so obviously I'm not going to the gym in person, but I am mentally here. So thanks you for coming to the gym mentally, the mental gym here, guys. Um, but yeah, so far I have been. I do have a 9 to 5 as a chemist, right? So I try if I'm tired, I do get on. So far I've been pretty consistent. I have a streak going, so I'm trying to keep it alive. But the holidays might be kind of tough, guys. It might get kind of challenging. Shrouded says, or Justin says, I followed you on GitHub. Thank you so much. Yeah, check out the some of my projects on there, and if you're learning, check them out, and yeah. Shrouded Data. I like what you're doing, keeping yourself accountable while studying. I hope reach whatever goals you set for yourself when starting this journey. Yeah, honestly, this was just a goal of just self improvement and taking on a new skill, right? I think it's easy to give up on things, especially when things are so accessible nowadays, and you can oftentimes outsource them to resources and websites and things like that. But I think you can never it never hurts to learn something new, right? Justin says overall time complexity is calculating the big O notation for each line of the OR function in the program. Yeah, so we learned about in chapter 3 big O time complexity, which is the worst case scenario for the function. So or the algorithm as a whole. So the algorithm on a local level, like on its each individual line, will have some sort of runtime for those lines, but overall those lines will depict through greater operations, uh, for lack of better terms, a general time complexity for its worst case, and we define it in that case in big O, if that made much sense. So how I often think about it is like think about it as like a bottleneck. Is you have a function within your algorithm that is slower than all the others. Well, that is probably going to be your bottleneck function where things are going to get caught up. So it can only run as fast as the bottleneck will allow, right? You can only have things pour out of a bottle as fast as the outlet will allow. Jeremy, thank you so much on the yes, congrats on 400. Congrats to you guys. You guys are truly the people that are keeping this going. It's all of us. We are all together on this. This is 400 family here. Angela, it's a bit hard to keep up with the lives because of the time difference, but it's Friday, Saturday here already, so I'll try. I know that is the really difficult part is it's because I have a 9 to 5 job, so I can only really stream after that. I have a commute like it's brutal. Unfortunately, I don't live that far, but it's just mass traffic and stuff. So it's just I lose so much time in all of that I only get about 2.5 hours of solid brain work before I have to go back to bed and reset after work. But the weekends I really try to and lengthen that in the day so we can spend some more time together here. But I appreciate you trying your best. Yes, I'm trying my best too to stay consistent here and lengthen my streams and stream. I'm going to try to stream tomorrow morning, early for me. It'll be Saturday morning. I'm going to try to do an earlier stream in the morning so we can get a little bit more of that. Those our East Coast subscribers on and our more of our also international. We have a lot of international subscribers as well, so we need to accommodate to everybody as well. All right. I missed chapter three. Well, the great thing is I have stuff on my stream that's still up. So we had a lot of great discussions on chapter three. We did 34 practice problems, as you can see from our left side of our screen in our Explorer tab. So got a lot of practice with Big O. All right, let's continue on, you guys. Sorry, I am stalling out here. We need to continue on. We need to keep reading. Okay, so when the sequence is indexed, there's a much more efficient algorithm for intuition. Okay, for any index j, we know that all the values stored in indices 0 all the way through j minus 1 are less than or equal to the value at index j. We know that all the values stored at the indices are less than or equal to the values at index j. Yes, right? If you have a list of 0, 1, 2, 3, 4, 5, and you're at the fourth element, well, that is greater than or equal to all the elements that precede it, j minus 1, right? Cool. So then we get that. This observation allows us to quickly home in on a search target using a variant of the children's game high-low. Hot cold here. We call an element of the sequence a candidate if at that current stage of the search we cannot rule out that this item matches the target. The algorithm maintains two parameters, low and high, such that all the candidate entries have indexed at least low and at most high. Initially, low equals 0 and high equals n minus 1. We then compared the largest value to the median candidate. That is, if the item data mid with index mid equals, okay, we consider these three cases. If the target equals data mid, then we have found the item we are looking for. And if the search terminates successfully. If the target is less than the midpoint of the data, then we recur on the first half of the sequence, that is, on the interval of indices from low to mid minus 1. Got you. If the target equals data, our target is greater than the midpoint of the data set, then we recur on the second half of the sequence, that is, on the interval of the indices of mid plus 1 to high. Exactly. So what this is saying is we have a target, and we initially will take the average of the data set or to try to find the midpoint somehow. So how exactly did they do that? So they initially set low equal to 0 and high to n minus 1. Okay, so you just take the average of the data set, then we compare to the mid to the target. Okay, cool. That seems very self-explanatory. So all you're doing is you have a data set of values. Let me go ahead and type this out here. We need to actually take some notes here. We are failing drastically on keeping up with our notes. So when you have like a data set, we'll say you have n right here is equal to a list of values. We'll say it's got to be sorted, right? So 5, 6, 7, 8, 9, right? So this is our data set. Our midpoint in this data set is going to be our low plus our high. No. N minus 1. So n is 5 in this case. So is this index? Oh, this is index. Yes. Okay, that's why. So don't confuse this, guys, with meaning like you literally take 0 as low and the value of n minus 1 as high. You do that actually, but no, this is you do that theoretically in this case, but that's not the right way of thinking about it. the low in this case is referring to the index value. The lowest index value in this current, at our first recursion of this binary search is going to be associated with this, right? If we put the indexes here, this is the 0, this is the first, second, third, and fourth. Or in the fourth, in this case, I'll say is n minus 1, right? So that being said, we're going to take our 5, we're going to add it to n minus 1, or our high, 9, and we're going to divide by 2. So that'll give us 14 divided by 2 is 7, and which, because this is an ordered list with a skip of 1, just like just going up of normal ones numbers, we have that, we can obviously see that is the midpoint visually. But so that's what it does. Now what it will do is we have a target. Now let's say our target is equal to 6, right? So what it's going to do is it's going to first recurse through this list. It's going to say, what's the midpoint? It's going to gather that information by saving it in this variable. It's going to say, okay, let's do a comparison. Is our target greater than or less than our, let's start with greater than so we can have that example. Is our target greater than our midpoint? Meaning that, is it 7, 8, above 7, or above 7? Is it 8 or 9 in this case? No, it is not. So we're going to then say, is it less than our midpoint? I think you would actually first, like it says, you first check if it is the item. So you would first say, is midpoint equal to target? No, 7 is not equal to 6. Then you say, okay, is it greater than target? Is target greater than the midpoint? No, 6 is not greater than 7 in this case. Well, that means just by default, target is less than midpoint, so we could probably just say else, then we already know. We don't need to make another statement to do a comparison. We can just jump right into our program or whatever we want to do to the value and probably split the list once again. We'll recurse back at that point. So else, recurse back, find midpoint of, in this case, it would be midpoint index. So I want to know how they do that. So you'd have to then create the new midpoint from 0 to midpoint, or n minus, what do they do to find this 2 index value, or in this the midpoint's index value? We'll find that out. All right, we got some chats here. Thank you, Justin, for the motivation for everybody. I appreciate you. Justin said, would you ever consider a software engineering or data science job on the side if you continue to learn programming? Definitely. I never saw yourself short of considering things that you might set yourself up for success. So, always keep an open mind to things, for sure. I think data science would be perfect for the type of work he already does. Yeah, I would love to, explore possibilities of those, paths, and, always take on new challenges and push yourself to do things. I would definitely, am interested for sure in all that kind of things. Those kinds of things. I agree. He's got a talent. Oh, you guys are so nice. You guys are really nice. Build your CNC. Thank you so much for joining. I appreciate you coming in. How are you doing today? Welcome to the channel. We are just checking out some data structures and algorithms in Python, doing some studying as a group here. All right. For those that are new, I have a Bachelor's of Science in Human Biology and a minor in Chemistry. I kind of focused on the physiological aspects, chemistry side of human biology, and on a cellular level. I really enjoyed the inner workings of chemistry and things like that, and so I became a formulation chemist right after college at a biotech company, and I've been there for a little bit while now, about 3 years, and I since 2021 when I graduated, and anyways, I'm just teaching myself Python here to gain additional skills and push myself to learn new things past college, and I also hold myself accountable with the stream and everything. Yeah. And this, yeah, so this data structure and algorithm book, it was free online. I found it online, but I also provided a copy in the Discord below, which is just, if you guys don't know, I have a Discord below. I recently made some improvements to it last night. I was up pretty late last night, making some adjustments to it and adding in some more features. Just of a, it's just an area where I've compiled all of my study resources into one location for the viewers and everybody to follow along for their own enjoyment or purposes, and also to just create a general community for sharing things and supporting each other. So yeah, please consider giving that a join if you're interested. Got like a hairball. Okay, so that makes a lot of sense. Is you just split, you find the midpoint, and then you just do high low on the midpoint until you kind of narrow down your value. So this algorithm is known as binary search. Okay, hold on. An unsuccessful search occurs if low is greater than high, as interval low high is empty. If low becomes greater than high, as the interval low high becomes empty. Got you. Meaning that we can no longer divide the list in half because our low point has become greater than our high point. Which is, how would that work? I thought they would become the same number as you hone in on a single value. Got you. So this algorithm is known as binary search. We give a Python implementation in code fragment 4.3 and an illustration of the execution of the algorithm in figure 4.5. Got you. So we'll get there. An illustration of the execution of the algorithm in figure 4.5. Whereas sequential search runs in O of n time, the more efficient binary search runs in O log n. So we were exactly right, guys. We were, that just proves that we're actually, learning this stuff. In chapter 3, we learned, how to classify these functions in their time complexity for the worst case scenario, or known as big O. And just before we even got down there, we were reading through what binary search was, and we were able to interpret that this was going to be a log n time complexity function or algorithm. Right? So this is a significant improvement given that if n is 1 billion, log n is only 30. We defer our formal analysis of binary search's running time to proposition 4.2 in section 4.2. All right, we got some chats here. Justin, thanks so much for joining. You found the mid index. 0 plus 4 divided by 2 equals 2, and 2 is equal to 7. Zero is equal to plus 4. So if you're starting at 0, you're going to 4. See, that's, Justin, I think that's what the misinterpretation I was making at first is. This isn't physically saying, no, it is saying, yeah, it is 0, right? So if you have 0 to 4, would be 4 divided by 2 is 2, so, and 2 is equal to 7. Yes, oh, exactly. So you'd be accessing, you're doing the index accessing with these values, and then you would access, midpoint is the, would be the index at this point, right? This is the index mid, the mid index, right, as it's applied here, because it's within the index. Exactly, Justin. Mid is an index value, not the value of the list itself. You use the mid to access it when applied to the data set, right? Perfect. Justin said the Discord looks great. Awesome. Yeah, I really tried to spruce it up a little bit to make it more enjoyable and more easy to follow for everybody. So, gotcha. and I added some stuff for like the Odin project. Although I haven't completed that, obviously I'm focusing on Python mainly. I did give that kind of a stab a couple months back. I did complete about half of it in about 2 days. Um, I really grinded through it, so or 2 3 days. So yeah. Builder your CNC said I wanted to learn Python, only use the MoviePy library. Been programming many languages for 4 decades. Now it's time to learn myself. Wow, that's a lot of experience. I applaud you so much for
Hello,
your
everyone.
experience. Oh, I just pulled up your channel. Wow, that's really awesome, Build Your CNC. Thanks so much for joining me. All right, Angel Lopez. I'll take a look. Gotcha. Okay, let's keep moving here. Um, all right, this algorithm is known as binary search. Okay, we talked about that. Cool. So the def binary search, we have data and we take target, low, high. Okay, cool. So we take in our data set, probably in the form of some list or array, maybe like a set, um, and then we have a target value that we get input. We have a low and we have a high. So we say if low is greater than high, we return false, meaning like that's our a breakpoint. In recursion functions, we're not looping directly, so we can't call break, but we have just this break here technically that will stop us from entering the recursion state or the next level of recursion. So interval is empty, no match. Got you. So else, right? If we can go ahead and do the find a midpoint between these two values, we're going to do the mid point with low plus high divided by what is this interval division of 2. If target is equal to the data at the midpoint, we return true. Else, if target is less than data at the midpoint, return the binary search for data, target, low, and then you just do mid minus 1 for the high. Ah, okay. Interesting. So else we return the mid plus 1 and then all the way to high. Got you. So this is exactly what we explained verbally when we read through these definitions up here. So this is for sure looking good. All right. All right. Where are we at? An implementation of the binary search algorithm. So low, we have an example here. So we have an array of numbers in order, right? So 2, 4, 7, and all the way to 37, but with no general skip preference. It looks like. Oh, actually, they go up by 1, 2, 1, 1, 3, 2, 3, 2. Interesting. I wonder if there's any actual pattern to this, but we have an array or list, and we have a midpoint that we found, which it would give us. So mid would reply with a value of 7. We would then call data at midpoint. So then we're not finding, we're not searching for value in data point, right? We are accessing a index value. The key to binary search, as it stated above, is a sorted and indexable list or data set. So we are accessing an index and then using that index of mid, we're finding the mid index and then applying that to the set to then find the value at the mid index, which is 14. We then say, okay, is our target less than our data point mid? Is our target less than 14? Let's say our target was 11. Okay, it would say no. We're going to go to this else statement. If it was less than 14, we're going to recurse again in binary search, right? We're going to call our function back on itself, apply the data set, apply the same target, apply the same low point, right? Because we're on this half of the list from low to the mid, and then for our high point, well, our high point is not the high point up here at 37 because we determined that that target is on the lower half of the list. So now we will just make our high point of mid minus 1 index, right? And then the same applies to the else scenario, right? If you have a value that's higher. So this makes a lot of sense. This looks good. I like this a lot, actually. It like makes my brain kind of feel nice. I don't know. I don't know when math kind of works like this and makes sense right off the jump. Now, when we try to apply it, that's a different story. So we should probably not speak too soon here. Okay, so then we have binary search. So used using recursion. Oh my gosh, recursion. We track. Oh, so hold on. Using recursion, we will track a high and low index value of the data set. Data set n, right? So this will be 0 index, so low to start index, or sorry, low is equal to 0, right, for index 0, and high is equal to n minus 1, right, because 0 indexed. Start is 0 indexed, right? Cool. So binary search, we're using recursion. We will track a high and low index value of the data set to start. Low equals 0, high equals n minus 1. We then calculate the mid point index value using our equation up here. So why did they use integer division here, and then up here in the example just use regular division? Because we don't want a half value, right? You need a whole value. So that's why they do this. So they do it divide by 2, but this will floor the function, right? This is written inside of a floor notation, meaning that for the value that we receive, it will be rounded down to the floor, to the near. So if we have an array with a odd number of indices, right? If you divide that by 2, you will get a half value, like 7.5. So we will floor that to 7 for this case. Okay, so that's what that means. Mid equals, I'll just copy this guy up here, like that. Like so. We will say note the answer is floored right? Round the round floats down, right? Perfect. Uh, gotcha. So the answer is floored round floats down. So use integer division when writing in Python. And we'll copy this. Awesome. Sweet. Let's get caught up on the chat here. Sorry guys, was deep in learning. So let me get caught up here. um, okay. I've been learning C# forever over again. It's been fun, and I hope to utilize it to make my own game. I'm guessing you're using Uni. Oh, gotcha. Awesome. I have been wanting to mess with Godot. I've never played with an engine before. Well, yeah. Me either. Yeah, me either, guys. Me either. uh, let's see here. Destiel, thanks so much for coming in. What field of Python you're planning on going into? Um, I don't know. This is if that was reference to me, this is I already am a chemist, right? So I'm just kind of learning for fun here at the moment and taking the pressure off of learning by keeping it fun, and it definitely helps. Jeremy Fuller, the 3D AI model generators dropping lately are crazy. I was watching a video called Trellis today. Yeah, I saw a couple of videos on that, and it's interesting. I wonder how many of these like companies are going to survive over the course of the next like 5 years that are making these things. Omar says, I love search algorithms like binary search. It's the sorting algorithms that have me suffering, especially when it comes to sorting strings. Well, I'm sure we're gonna be struggling too then when we get there. So thanks for giving me the heads up. So we then calculate the midpoint. So then we'll say play a game. Lastly, using conditionals, evaluate if compare the target value or target element to the element at the mid index. So it would be like list mid, right? Like that. So if target greater than list mid, or I'll say n mid, right? Or we'll say list rather. I like list. Okay. Lastly, using conditionals, compare the target element to the list at mid and okay. And then we'll say if conditional based on which and if target less than list mid, right? So So if condition either conditional is met, if either conditional is met, we will call a recursive call recurse through the data set, recurse through the data set how can I'm trying to say this without sounding too like technical. So recurse through the data set we call recurse through the data set for the side satisfied half of the data set. Does that make any sense? So like lastly, using conditionals, compare the target element to the element at the mid index. If target is greater than mid list, right, and if target is less than list mid. If either condition is met, recurse through the data set for the satisfied half of the data set per conditional. And then we say using mid minus 1, using mid minus 1 as either high or low for the satisfied. Right. So compare the target element to the element at the mid index. So I'm going to take this and I'm going to ask Jivity, the almighty orb, to make this summarize my my explan, my definition of a binary search in simple terms. Okay. So binary search. Start with a search this method unless it works by dividing list in half repeatedly. Start with 2 pointers. Low being okay. Got you. Find the middle. Compare the target value. Okay, I like that. Let's take that. And then I'm gonna put that here. And then I'm gonna take these back. Oop, like so. And I'm gonna go do this one. Two, 3. Oh. And then 4, like that. Cool. Now let's go Shift Command Z. See what that looks like. So we have sorted data sets, sequential search, binary search. Start with 2 pointers. Nice. So then what I'm going to do, cool. I like that. Um, you learn fast. I see you learn fast. This takes a little over a year to learn in college. Well, yeah, awesome. Cool. That sounds great. Dustil, I know, man. I have been in college for a few years, and this guy is learning much faster than I have. You guys are too nice. I don't know what to say to all your guys' compliments. It's honestly, I don't know. I guess you guys are just being honest. If I'm learning quick, I'm learning quick. But just also know that I I kind of like I say um I I've already graduated college. I have a little bit of experience in the field already. And so also college has you learning a lot of different things all at once. And I'm only deep diving into a single topic. So I think there's also a comparison of apples and oranges going on where college is really spreading you out very thin across your time there and moves you on quite quickly, unfortunately. And so you may have gaps in your knowledge, you know, just by nature of college and how fast you have to continually move on. Now, if you obviously grind really hard and fill in those gaps with just mass studying, just hours, right, then good on you. But if you're a normal person that has to have a job to pay for college, has a family, has friends, so wants to experience what you're actually paying for in college, going to sporting activities and whatever else, you're paying for those fees, going to the gyms and the co-ed stuff, all that stuff. You're paying for all that, so you get to want to enjoy all that. So I think it's unfair to try to force all of this. It's just not enough, unfortunately, not enough time and too much material. But we're just talking about one topic here, and so we're diving in this, um, you know, uh, at just a different perspective. I feel. uh, I feel as if university took all of those unnecessary classes. It would have taken tops 2.5 years to graduate. Exactly. Exactly to my point is that they provide you all of these other classes. Now it's way better than high school in the fact that you're more tailored to a niche that you're actually interested in. But still, you are obliged to take these other classes, and just to I think it's a money grab at the end of the day too, right? You're paying for this kind of thing, so unfortunately you have to be there 4 years on their idea so they can get their money's worth. I completely agree. I feel like general maths and English can be important, but you should only really ever need your classes required for your major. Exactly. Yeah, that's an interesting point. That steel. Not saying people shouldn't go to it. By the way, yeah, yeah, for sure. I think it's been a valuable experience for me, and I don't regret it. If anything, I have just realized that the importance of self-teaching. That's true. Exactly. And I also think that I am 25, going on 26, so I am kind of more in that graduate age. If I were back in school, so you also you do when you get older. I think, and I'm not too old. I can't say I'm older, but when you get older, you do kind of um, you learn more skills about how to self teach yourself. I think than you were taught before because you're no longer reliant on a teacher. You have to teach yourself. But obviously, AI has helped that tremendously and made it a lot easier. But yeah, is the teaching yourself part is what is I think is just not taught because it's not really needed because you have teachers in school. Uh, yeah, you got a great point. You're taking a much deeper approach to learning Python when in college you can literally be learning 2 to 3 different programming languages at once, which is rough. Exactly. Like I've seen some of these people, some CS major schedules, and they have like Python at 9, then they'll have C at like noon, and then they're doing like you know, some other just random like IT infrastructure thing at like 3 o'clock. And it's like, yeah, some of these concepts might overlap, but what if you just did Python 3 hours instead? Like, how much could you actually learn in general rather than like breaking your flow state in terms of your learning, going from class to class on different topics? What if you just, like, I don't know, like, that's what's an interesting approach and take. Okay, so I'm gonna ask Jippity to take this and give me a Python code in Markdown. Give me give me this binary search example in Python Markdown format. Um, paste it here. I keep drinking this lemonade and it's going down the wrong pipe. What's going on? I'm like a mess. Okay. Paste it here like that. Whoops. We need to bring all of this in. Like that. And then do I need to close this? Like that. And then shift V. Cool. All right, cool. Now we got that example pasted right in there. So that is awesome. We have awesome. uh, Muna says, how's it going? Yes, we did finish chapter 3. We completed all 34 reinforcement problems at the end of chapter 3. So if you guys are wanting to get access to these answers to the end of chapter 3 practice problems going over big O, now these are my answers. They could not be 100% right. I did have maybe a little bit of struggle with a couple of them. I think there was one where me in the chat on this one, I think on 31, we were going back and forth on what the time complexity of these were, and Jippity was giving us weird answers, and there was some scenarios that weren't exactly specified in this problem that we were kind of some end cases or edge cases rather that we were not that weren't super clear. So we were having a little. So obviously take things with a grain of salt, but for the most part, I think we have some pretty solid solutions to the chapter 3 problem. So we did finish chapter 3 and we are moving on here into chapter 4. So we just learned about binary search and we have a really nice chapter 4 notes. I think someone provided me some a suggestion to use markdown rather than the txt like I did in chapter 3. I used txt, and then now we're using markdown, so we're getting a really nice formatting going on here. So yeah, it's really cool. All right, moving on to the last illustrative example here is the file system. Okay. Modern operating systems define file systems directories, which are also sometimes called folders in a recursive way. Namely, a file system consists of a top-level directory and the contents of this directory consist of files and other directories, which in turn can contain files in other directories, and so on and so on. The operating system allows directories to be nested arbitrarily deep as long as there is enough space in memory, although there must necessarily be some base directories that contain only files, not further subdirectories. A representation of a portion of a file system is given in 4.6. So like just in any, right, you have just nested file systems. So I think we're going to start getting into um, like this when I look at this and I think of programming, I see like trees, right? And so we have levels of trees. I don't know, like again, I've only seen like just TikToks and reels about trees and things from the elite code people, but um, from my understanding and from like a genetics point of view and like from other science, is you have these levels of inheritance, right, and relation, and then I believe as you get further and further out with recursion, you would do becomes exponentially larger, right? In terms of time. I'm not sure exactly, but we'll see. That might not make much sense, but let's just continue. Given the recursive nature of file system representation, it should not come as any surprise that many common behaviors of an operating system, such as copying a directory or deleting a directory, are implemented with recursive algorithms. In this section, we consider one such algorithm, computing the total disk usage of all files and directories nested within a particular directory. For illustration, figure 4.7 portrays the disk space being used by all entries in our sample file system. We differentiate between the immediate disk space used by each entry and the cumulative disk space used by that entry and all nested features. For example, the CS016 directory uses only 2K of intermediate space, but a total of 249K of cumulative space. Okay, so we have a figure 4.7 here, which portrays disk file space used by entries in our file system. We differentiate between immediate disk space used by all entries and cumulative disk space used by all entries in that nested features. So cumulatively, this has this much disk space, which is summed all of these disk spaces, right? I believe. But inside of here, you only have 1K of disk space being used up. So exactly, that makes sense. So you have a file here, which inside of our directory has its own sort of disk space, but total it has this much because it's this sum. So looks like just a simple folder actually takes up 1K in this case, but this one has a 2K. So interesting. Let's move on. All right, let's keep going here. The cumulative disk space for an entry can be computed with a simple recursive algorithm. It is equal to the immediate disk space used by all the entries plus the sum of the cumulative disk space used of any entries that are stored directly within the entry. So it is equal to the immediate disk space used by the entry plus the sum of the cumulative. Okay, gotcha. For example, the cumulative sum of the disk space of CS016 is 249K, right, is that right here, because it uses 2K itself, 8K cumulatively in grades, 10K cumulatively in homeworks, 249K used in, or sorry, 10K cumulatively in homeworks, and 229 in programs. Pseudocode for this program is given in code fragment 4.4. So algorithm disk space, input, a string designating a path to a file system entry. Output, the cumulative disk space used by that entry and any nested entries. Okay. Total equals size of the path. If path represents a directory, then for each child entry stored within the directory path, do the total plus disk usage of the child. Return total. Okay, gotcha. Python's OS module. Python, to provide a Python implementation of a recursive algorithm for computing disk space usage, we rely on Python's OS module, which provides robust tools for interacting with operating system design during the execution of a program. This is an extensive library, but we will only need the following 4 functions: os.path.getSize of the path, os.pathIsDir of the path, os.listdir path, and os.path.join path and file name. So the path getSize returns the immediate disk usage measured in bytes of the file or directory that is identified by the string path. The os path is dir returns true, so it returns a boolean if it's a directory, otherwise false. The listdir path returns a list of strings that are the names of all entries within a directory designated by string path. In our sample file system, if the parameter is this file path, the user returns all of the file names. Okay. CS252 here. Oh, directory names returns a string that are named all entries within a directory. Okay, so even if it's all entries, so if it's a file or a directory itself, got you. And then the path join, compose the path string and file name string using an appropriate operating system separator between the two. The / character for Unix and Linux system, and the / character for Windows. Return the string that represents the full path of the file. So the path.join takes in a path and a file name, compose the path string and the file name using an appropriate operating. Oh, so it joins the two together with the file. Okay, like this, like it adds the files inside of it. So does it basically create that file inside by creating that string? Oh, it just creates a path, a string, right? So then you could take that string and then use it, like if you created a file or something, right? And you wanted to access that file. Okay. Python implementation. We use the OS module. With the use of the OS module, we now convert the algorithm from CodeFragment 4.4 into the Python implementation of CodeFragment 4.5. Okay, so we have import OS here. We have def disk usage, and we take in some path. We return the number of bytes used by a file or folder of any of its descendants. So total is we get the size of the path using the getSize function. We if it's a directory, if the path given is a directory, for every file name in the directory, right, we call child path variable is the okay, oh, gotcha. So we want to access every file name in the directory. We create a child path, which is just the the file pathway of those individual files within the directory, and then we create that child path and return them with a print statement here, or print them out individually. But we do total plus equals disk usage on the child path. Okay, so then you call it further until you go all the way down to where there's no more directories. Right, and there's only files, and then you're at your base case and you return total. This makes a lot of sense, right? So all we're doing is just going down deeper and deeper and deeper into files until we don't reach any more directories via this boolean, and we are only now in this loop. And once this returns false, we will print out the some sort of print statement here. I'm not really dot format. I don't really do the dot format. I use fstring, so I'm not really familiar. We format total with uh, I don't even know what this means. Is this some sort of rounding preference? And then path with the path. And then you just return the total amount of file space taken up by all of the directories and paths, all the directories and files within this original pathway. Interesting. Jordan Woods, thanks so much for coming in again. Good to hear from you. How you doing today? Welcome. All right, we got Justin. Hey man, I'm gonna head out. Good luck and have a great night. I'll try to tune in for the next stream. Yeah, no worries. I'll try to. I'm gonna definitely be here tomorrow on Saturday. Like I said, I'm gonna try to do um, an earlier stream just to accommodate more of the East Coast and international folks because I do stream later in the night and early in the morning for them. So yeah, tomorrow we will be back. So be here tomorrow. I appreciate you coming in for today though. This I'm not ending though. I'm not ending right now, but you in particular, thank you for coming in. All right. Recursion trace. To produce to produce a different form of a recursion trace, we have included an extraneous print statement within our Python implementation, code line 11. Okay, right here. This is what it does. The precise format of the output intentionally mirrors output that is produced by a classic Unix/Linux utility named DU for disk usage. It reports the amount of disk space used by a directory and all contents nested within, and can produce a verbose report as given in figure 4.8. Our implementation of the disk usage function produces an identical result. When executed on the sample file system portrayed in figure 4.7, during the execution of the algorithm, exactly one recursive call is made for each entry in the portion of the file system that is considered. Because the print statement is made just before the returning of from a recursive call, the output shown in figure 4.8 reflects the order in which the recursive calls are completed. In particular, we begin and end a recursive call for each entry that is nested below another entry, computing the nested cumulative disk space before we can compute and report the cumulative disk space for the containing entry. For example, we do not know the cumulative total for entry users RT courses CS016 until after the recursive calls regarding entries graded grades, homework, and programs are complete. So we access users C06, but it's not actually fully read until after all of the files within this full directory are read. So that's what's going on here. Got you. Right, because what we do is we go through the child path. We do the child path first and find the disk usage of the child path. So eventually, if is dir, we go into it. If it's not a directory, what do you do? So what if it's not a directory? Like what if you start with the file? So you get size of the total path provided. If that path is a directory, go ahead and get the size of all of the files within the path. Okay. A report of the disk usage for the file system shown in figure 4.7 as generated by the Unix/Linux utility DU with command line options -AK, or equivalently by our disk usage function from code fragment 4.5. Analyzing recursive algorithms. In Chapter 3, we introduce mathematical techniques for analyzing the efficiency of an algorithm based upon an estimate of the number of primitive operations that are executed by the algorithm, right? We learned about primitive operations, which are the number of basic functions and things applied to um, the uh, the algorithm. But these functions, when under certain large input values, can perform at various rates, and we determine using big O notation the relationship of these operations for the large input sizes. In this section, we demonstrate how to perform this type of running time analysis to recursive algorithms. With a recursive algorithm, we will account for each operation that is performed based upon the particular activation of the function that manages the flow of control when so with a recursive algorithm, we will account for each operation that's performed based upon the particular activation of the function that manages the flow of control at the time it is executed. Stated another way, for each invocation of the function, we only account for the number of operations that are performed within the body of that activation. We can then account for the overall number of operations that are executed as part of the recursive algorithm by taking the sum over all activations of the number of operations that take place during the individual activation. As an aside, there is also the way we analyze a non-recursive function that calls other function within its body. This is also the way we analyze a non-recursive function that calls other functions within its body. Got you. So basically this went over, like, it talked about this earlier about, like, when you call functions within the body of other functions, it kind of creates that data frame within the Python framework and kind of stops at that instance, runs the other program, and then returns back at that point and then continues forward. Yeah. To demonstrate this style of analysis, we revisit the 4 recursive algorithms presented in section 4.1.1 through 4.1.4: factorial computation, drawing an English ruler, binary search, and computation of this cumulative size of a file system. In general, we may rely on the intuition afforded by a recursive trace in recognizing how many recursive activations occur and how the parameterization of each activation can be used to estimate the number of primitive operations that occur within the body of that activation. However, each of these recursive algorithms has a unique structure and form. So we're going to go back to the factorials now. It is relatively easy to analyze the efficiency of a function for computing factorials. As described in section 4.1.1, a sample recursion trace for our factorial function was given in figure 4.1. To compute factorial n, we see that there are a total of n plus 1 activations as the parameter decreases from n to the first call, in the first call, to n minus 1 in the second call, and so on until reaching the base case with parameter 0. It is also clear that given an examination of the function body in code fragment 4.1 that each individual activation of factorial executes a constant number of operations. It is also clear given an examination of the function body in code fragment 4.1 that each individual activation of the factorial, so this is the code fragment, I think, right? That each individual activation of factorial executes a constant number of operations. Therefore, we conclude that the overall number of operations for computing factorial n is O of n, and there are n plus 1 activations, each of which account for O of 1 operations. Oh boy. All right. Sad the Bad says, recursive, wow, I'm having the biggest deja vu because I just did this in my computer science 2 final 2 days ago, but it was in C++. Now I'm finally a graduate at community college and will be at 4-year. Awesome, congratulations, that's super cool. Thanks so much for joining us, Sad the Bad. I appreciate you coming in. Soon, so beginning of next year. Also, hey Michael, it's been a while, hope all is well. I look at recursions as like a rocket beginning liftoff and then resetting. Can you explain that analogy a little bit better? I like that. Can you explain that in more detail? Thanks so much for coming in today. I appreciate you stopping in. Okay. So it is relatively easy to analyze the efficiency of our function from computing factorials as described in this. A sample recursion trace for a factorial was given. So to compute factorial n, we see that there are a total of n plus 1 activations. As the parameter decreases from n in the first call to n minus 1 in the second call, and so on until reaching the base case with parameter 0. N plus 1 activations. So is the 1 in this case just the call of the function again? It's also clear, given an examination of the function body in code fragment 4.1, that each individual activation of factorial executes a constant number of operations. This executes factorial of n which runs in constant time. No, we return n times factorial n minus 1. So I'm going to take this, I'm going to plug it into the Jippity, explain this, break this down. I am having trouble following. I'm not afraid to admit defeat sometimes, guys. I can admit it. Let's break down this step by step. So the goal is to analyze the efficiency, time complexity of a recursive function that computes the factorial of number n. The factorial of n factorial is calculated as n times n minus 1 times n minus 2 times n all the way to 1. The base case, 0 factorial is equal to 1. The recursion works as follows. Factorial n equals n times factorial n minus 1, exactly. This process repeats until the base case is reached of factorial 0 equals 1. Recursive calls and activations. When we call factorial n, the function invokes itself with factorial n minus 1, factorial n minus 2, and so on until each of these is an activation of the function. Gotcha. So when we call the recursion of the function, that is the activation. Number of activations. The parameter n decreases by 1 in each recursive call until it reaches 0. So there are n plus 1 activations in total, 1 for each value of n. 0, 1, 2. Why do you have n plus 1 activations? So you'd obviously do all of n minus 1. So if n is 5, it'd be 4, 3, 2, 1. And then obviously you have 5. And plus 1 activations in total. Does the 0 count as 1, 2? Meaning 1 or 0 factorial? Work done per activation. When we examine the body of the recursive function, each activation of the function performs a constant amount of work. A multiplication operation, a comparison to check if n is equal to 0, so the factorial function itself runs in constant time because all you do is check if n is equal to 0, you return 1, else you return a multiplication. But when you call an activation of the recursion of factorial itself, that's when you start to mess with the time complexity. And so, yeah, okay, got you. Let's get caught up on the chat. The example of a rocket when it's getting ready for liftoff, when it has a timer set like 5, 4, 3, 2, 1, and then it plays, and then an output liftoff. After the liftoff, it resets back to, I think, ascending order 4, 3, 2, 1, 0. N minus 1 means descending as like a rocket being ready for liftoff. Gotcha. Oh, okay. So the liftoff is the return. So you go 5, 4, 3, 2, 1, 0, liftoff, and the liftoff is the return. So um, 0 factorial is 1. So then, would you ever get down to 0? So 5, right? 0 factorial is equal to 1. So if you got down to 0, you'd just be multiplying by 1. So why are we n minus 1? Gotcha. Okay. So there are, what's really tripping me up is why there are n plus 1 activations. That's what I don't get. Is why do we have n plus 1 activations? So it says work done per activation. It possibly means it's O 1 time. It does not depend on n, so it's small and fixed. The work total done. There are n plus 1 activations. Each activation takes constant time, so it's n plus 1 times O of 1, which is O of n. So I just want to know, why are there n plus 1 activations? The initial activation and then the call of factorial itself. Now if I I think that's what it is. So if we had the initial activation is just n, right? And then you have n plus 1 activations because you have an additional call of the function itself of n minus 1. But obviously this is some constant operation, so we don't really care about it. In like time complexity standpoint. Louis says, I get what you're saying. I would say that if you would end with when n equals 1, return 1 and have n activations. So is the n plus 1 activations, does the 1 represent the the recursive call within the body of the initial call? Great question. Let's clarify the n plus 1 activation step by step. The n plus 1 activations represents the total number of times function's factorial is called during the computations of factorial n. This includes the initial function call, the recursive calls made until the base case is reached. yn plus 1. To compute factorial n, you would have to, you first calls n, and then recursively goes factorial n minus 1, factorial n minus 2, and so on. Finally, the function reaches the base case of 0 and terminates the recursion. Got you? So there are n recursive calls, okay, because you have to recurse each value of n, plus one additional call for the base case. This adds up to n plus 1 total activations. Calls. Okay, so you just add up all the calls of the factorial function. Got you. And then it's got you. Okay. What about the recursive call and the function body? Each recursive call is triggered by the current activation of the function as part of the body. For example, when you call factorial n, it immediately makes a call to factorial n minus 1 if n is not equal to 0. And so on. The chain of calls is the total number of activations ends up being n plus 1. Got you. So exactly. Cool. All right. Let's keep moving on here. Inches. All right, cool. In analyzing the English ruler application from section 4.1.2, now I did not take good notes on this one, you guys. This one was kind of tricky to wrap my heads around, the English ruler one. We consider the function, we consider the fundamental question of how many total lines of output are generated by initial call of draw interval C, where C denotes the center length. So we consider the fundamental question of how many total lines of output are generated by the initial call to draw interval C, where C denotes the center length. This is a reasonable benchmark for the total efficiency of the algorithm, as each line of the output is based upon a call to the draw line utility. Each recursive call to draw interval with non-zero parameter makes exactly one direct call to draw a line. Some intuition may be gained by examining the source code and the recursion trace. We know that we call to draw interval C for C is greater than 0 spawns two calls to draw interval C minus 1 and a single call to draw a line. We will rely on this intuition to prove the following claim. For all values, for C is greater than or equal to 0, a call to draw interval C results in precisely 2 to the power of C minus 1 lines of output. We provide a formal proof of this claim by induction. See section 3.4.3. In fact, induction is a natural mathematical technique for proving the correctness and efficiency of a recursive process. In the case of the ruler, we note that an application of draw interval 0 generates no output, and that 2 to the power of 0 minus 1 is 0. This serves as a base case for our claim. More generally, the number of lines printed by draw interval C is one or more than twice the number generated by a call to draw interval of C minus 1. More generally, the number of lines printed by draw interval is one more than twice the number of generated calls to draw interval C minus 1, as one center line is printed between two such recursive calls. By induction, we have that the number of lines is thus 1 plus 2 times 2 to the power of C minus 1 minus 1. See, this one, the book does a really, I don't know, maybe I'm just dumb or whatnot, but the book is really hard to follow for this example they provide of the drawing English ruler. Obviously, this is the first. We're just getting into chapter 4 here. We're on day 2 of chapter 4, so we are still learning. But that's my first. The draw ruler one I'm struggling with. All right. The proof is indicative of a more mathematically rigorous tool known as recurrence equation that can be used to analyze the running time of a recursive algorithm. That technique is discussed in section 12.2.4 in the context of recursive sorting algorithms. Interesting. All right. So I'm gonna, I think what I'll do is in some spare time, I'm gonna watch a video on an example of the drawing English ruler. And I think I'll have to like see a physical representation of it being broken down. We have the code up here, right? We have this is the code of the physical English ruler. So we have a draw line function, which takes in a tick length and a label that has an optional parameter of nothing. So we have a line variable which takes in just a hash mark and then multiplies it by the tick length to create a tick length, right? Or create a line, right? And then we apply a label if it's given. We have another function here called draw interval, which takes in the center length. So if we want to draw an interval with a center length, we first make sure that center length is positive, right? We want to stop if the length drops below 0. We call draw interval, so we call it recursive draw interval call on the center length minus 1. So what this was going to do is it will then draw a line of that reduced center length, right? Because we have draw interval here and we have a draw line happening in here. We're going to call it twice more. So we're going to print within each call of the original sorry, I know this is getting confusing, but within each call of draw interval, we are printing three lines, right? No, we're printing one line and we call draw interval twice for center length minus 1. So then okay, so let me bring up like what is it? Paint? What is it called? Not passwords. Draw. What's it called? Oh my gosh. What's it called? Whiteboard. Okay, so this is what I think I'm starting to kind of understand here. So we have I'm gonna try to solve this, see what's going on here. Let me make this smaller. Okay, I'm using a magic mouse, guys. So this is gonna be rough. Just take that with a grain of salt. All right. So we have a draw line, which all it does is just draw the line that's provided via tick length. And so what we're going to do is we have a center length given to a draw interval function. So we call our function right here. This is our first call to it, right? We will then draw one line, and we will call two more functions, right? So we draw one line, and we call two more functions. Each of these functions will draw one line of one size less than the previous line. So let me go back here and make this 3. So this function is going to call, these are going to draw a line of 2. Now this is going to call two more functions because we're not at the base case yet. Right? These are going to call two more functions. These functions are going to print one line each. Right? And then I think that's where we end, right? Because now our center length is going to be 0. It will not call another function because center length is going to be center length minus 1 is 0. So this is where our representation. So we're going to get a center length of 3. So it'll look like this: center length of 3, two outside lengths of 2, and then four outside lengths of 1, like that. Did we just create a pyramid scheme? What's going on, guys? Oh! So we have our center point here of 3. We have our 2 calls here for 2's. And then these are producing a single line each for those single 4 calls for our 1's. Right? I think that's what it is, right? So if we go look at this, we have a center length, and the draw interval will 3, 1, 1, 2, 1. So no, I think we have the printing happening in the wrong order, right? So we need to get the printing happening. So the interval would happen here of 3, or this is for one with a mid space of 4. Oh, wait, hold on. I'm sorry. Back up, back up, back it up. Right? This happened. I think this gets sandwiched in between these two values. I'm not. Hold on. Let's keep going. Um. Eclipse S. No, I do not. I do not. I just do this out of my free time, and I enjoy spending time with you guys and interacting. It's fun for me to talk with you guys. It helps me be social, and also I really enjoy learning this. This is a hobby for me. If the YouTube channel ever develops, so these streams, do see reap in some little bit of value, that's fantastic. But no, I don't accept any uh, keep your funds, you guys, apply those to your own educations, to your own resources. Invest in yourselves. Don't, where you're just you being here, spending time with me. Time is extremely valuable, right? So just you being here alone is enough. So I appreciate you guys being here. So, and for those that don't know, my name is Michael. I'll just do a quick intro. I like to just do an intro every once in a while. My name is Michael. I graduated college back in 2021 with a bachelor's of science in human biology and a minor in chemistry. I really focused and was really liked the chemistry aspect of kind of human biologies and cells, dealing with like proteins, uh, cross-functional membranes, all that kind of stuff. All those kind of cellular level biology was really interesting to me. I was kind of on the lines of like medical school, dental school, but just I started really getting into chemistry. I was an undergraduate teaching fellow. I also was the general chemistry lab instructor for my college. I provided a ton of hours of studying and resources for chemistry. And anyways, after I graduated college, uh, I right after I graduated college, I got hired as a formulation chemist for a biotech company, and I've been there ever since. I've been working there for 3 years now, and it's been great. And I have a lot of instances in my work where I have to hand calculate and use my own intuition and interpretation for um, chemical matrices, balancing theoretical concentrations of large bulk products, and making sure I hit all my targets for my desired testings. And used in clinical diagnostics for patients, patient testing, and giving them accurate results. So I anyways, I thought I think it would be great to have a computer to kind of do these things for me. So that kind of did a deep dive into what is computer science and how can I learn how to program. So that was back in the end of May, beginning of June of 2024. Since then, I started the CS50P course, the Harvard's CS50P Python course online through EDX. I completed that very part time over the summer of 2024, this past summer. And then I kind of really started creating the channel and getting into programming once I completed that final project in that course. It really sparked a fire to, oh wow, I can actually build things with this, and I can really do this. So I created the channel to document my progress and help others that might be on a similar route as me, or learning along as well, self-independent, whether you're in college or not. Just creating a community of other people similar, or maybe more advanced. It doesn't matter. It was just and then just also to hold myself accountable, and so something I can look back on and say, wow, I actually really did improve, and I have something to show for it, and I have these other resources I can going back on. I have to go back and edit all the videos I make, so I'm hearing all the material over again. I'm talking with you guys for 2 3 hours a night on the weekends, 4 or 5 hours to about this material. So just day after day, hour after hour, we're just sticking this in our brain, just boom, 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 hammering it in nail after nail until it's just stuck in there. And yeah, so we're just taking all the pressure off of learning here, creating. I think that computer science has become fairly competitive with, off with the pay scales of things and with the job market, and I think it's kind of lost its touch of, from what I've seen, it used to have a touch of camaraderie and, especially like sharing and things like that. And um, this channel helps to, maybe change that and just make learning this fun rather than a chore, maybe because people, oh, I have to get a job, I need to learn, I need to study. But no, it's I need to study because I want to study and I want to get better, and I want to, it's fun for me. So exactly. All right, sorry about that rant. Let's get caught up on the chat. Theed says, sometimes I ask GPT to explain some text for a dummy with analogies. Always works for me. That's a good idea, actually, to maybe like use an analogy example. That's a good way to do it. Thank you, Theed, for that suggestion. Rajil says, what's the book title? We are currently working on data structures and algorithms in Python. And what this is it's just a textbook going over DSA and Python, as you could tell. It's a pretty challenging textbook. We've been breaking it down. We're on chapter 4 here, and then we've been doing the reinforcement problems at the end of the chapter. So as you can see, we have quite a lot of problems that we've completed so far live on stream. Almost probably like upwards of like 50 problems. So we've done a lot so far, but we are on chapter 4 now, learning about recursion. And yeah, thanks so much for joining. So also, guys, I have created a Discord linked below, which compiles all of my study resources from my personal notes to my PDFs of these books to other online Harvard CS50P, just a kind of a roadmap of what I've done so far in the Discord. Completely free. Again, nothing to charge for there. I'm a beginner. Not I just want to create an area for you guys to also access all the information. All right. So sorry, I'm talking a lot. Losing my breath here. All right. Mike P. Funk, thanks so much for joining, leaving some comments, leaving a lot of messages. I've been reading them here, giving a lot of good insight. Thanks so much for the support here. I appreciate you joining. Um, uh, Sorry, getting caught up with the chats here. There's a lot of them I missed on. I'm slow. I'm sorry, guys. um, uh, it's like that scene in Office where Michael draws a pyramid to explain. That's exactly what I was referencing. I'm so glad someone get it. It's like you have me, or you have him, and then he recruited me, and he recruited Tom, and then I recruit Jim and Dwight and Ryan, and then all of us are together, and then it's not a pyramid scheme. I've probably watched The Office, um, like probably from start to finish like 4 or 5 times, but not start to finish. I've seen a lot of the episodes probably 10 plus times. I actually just started the Big Bang Theory over again last night after the stream while I was working on the Discord. I like the Big Bang Theory too. I That's kind of a nostalgic one for me from my teenage years, high school. Um, Yeah, Mike P Funk suggested Jupyter notebooks. Yeah, I've heard of some stuff about Jupyter. I honestly don't know too much. We were using TXT to take our notes, and then we were suggested by someone in the chat to use Markdown. So we started using Markdown. So maybe eventually we'll transition over to Jupyter. So yeah. Um, you want to use pandas and NumPy. Yeah, someone else came in the chat earlier today and asked us when we were going to try to take a dive at pandas and NumPy. We are going to try to learn those packages or libraries as well. They are going to be crucial for Python data science, especially in my field. So we're going to take a stab at those. But I'm just trying not to open up too many projects at the moment. I want to get through some stuff. Um, you know, I know, but we just have such a long way to go through this book that I don't want things to get too monotonous here. So I want to keep, that's why I like to do the projects in the back half. But let me know what you guys think. Like, would you prefer if we kind of jumped around or just rather start a book and finish a book? Or or do you guys mind jumping from book to book, like doing Tuesdays, Thursdays, DSA, Wednesday, Thursdays, Friday, Fluent Python? Maybe to shake things up could help. What do you guys think? Um, is there any computation being used to support you or your peers at work? Jeremy, you mean like, do we currently use any like computer systems at work? We heavily use the Microsoft Office, as every other. We, I'm pretty good at Excel. I've got a lot of hours in Excel, and I currently do all of my small business work in Excel as well. So, but yeah, we use Excel. So, I would like to maybe, if there's an opening in my job and I get fluent enough in Python and data science and stuff, maybe apply for like a chemistry data science position or something. I don't know. It's really interesting. Um, I always ask Chat. Jordan says I always ask ChatGPT to explain it like I'm 5 and give me examples so I can visualize it. Awesome. Any sci-fi show, Rex? Well, Big Bang Theory is not too. They talk about sci-fi a lot, but it's more just reality. It's not reality. It's a just sitcom, right? Sci-fi Rex. Um, I don't. I I was watching. I was watching. I got through like up to season 5 of House MD, but the show gets kind of monotonous after a while, with the main character, to be honest. But it was pretty good. It's pretty good for the first little while. It's medical though, but not sci-fi. But Jordan Woods, I've been wanting to watch The Office. It's killer. I love it. Yo, Austin, thanks so much for joining. I appreciate you. Angela used to use pandas so much in her last job to clean spreadsheets. Wow, awesome. Well, you'll definitely be my resource and my go-to for questions then. I'll need you for sure. I will probably have to use pandas somehow within our small business manager to create those spreadsheets for our reports, income statements, all that kind of stuff. So, anyways, I think we're kind of getting it, right? We were able to do this. Draw ruler, draw line. So yeah, so we were able to create these tick marks, and then the ruler will place those in their orientation, right? So it definitely helped to actually draw out what was happening in these code lines from code line 8 to 13 here, right? Right, because for every call to the draw interval, we call draw interval twice, and then we draw a line once. So for every this represents a call, right? This represents a call. Every line here represents a call to the draw interval. I'll put a little C here to help clarify, and then I actually physically drew out the hash marks for each section, right? Because it's the length minus one, center length minus one. So if we had a center length minus of 3, we'd print out 2 center lengths, and then we would print out 1 center length 4 times for each of those, right? Cool. Yeah, so drawing this definitely helped me understand what was going on in this. I read this the first time, guys, and I'm gonna be honest, I was like, I'm never gonna come back. This really was like rough to read the first time yesterday, but today it felt a lot better. So we can break this down with this recursion trace diagram. So we have a draw interval of 3, right? Exact our example here. We call draw interval 2, which is the n minus 1 or 3 minus 1, and we call it again here. And with each of these draw intervals, we go down even one further into each one. So it gets drawn. So when we call draw interval, we draw a line. When we call draw interval again, we draw a line. When we call draw interval again, we draw the line, right? So we end up with, we'll draw a 2 line. And then for the other half. So this just demonstrates the single half. So what it's showing right here, you guys, is just this half. I'll try to do it like that. It's showing only either one of these sides. And then you can see the previous pattern repeats down here. That's what's going on. So we get 2 single hashes, we get 1 double hash, and we get 1 triple hash. And then it repeats on the other side. Exactly. We drew this out perfectly. Awesome. Look at that. Look at that, guys. Look at that. We are. Oh, let's get the lava lamp shaking up. Shake up the lava. I don't know if you guys can see if it's like focused or not. Ooh. I need to get some better lava lamp. I want to get like the room filled with lava lamps, like big ones, but lava lamps are pretty expensive. Okay, that helped a lot. Hopefully that helped you guys as well with this kind of diagram example. Okay, we just read this one. Okay, we're on the binary search. We're performing a binary search. Okay, considering the running time of the binary search algorithm as it's presented in section 4.1.3, we observe that a constant number of primitive operations are executed at each recursive. Okay, let me go back down here so I can see this function. Okay, we'll go to here. We'll locate it for here. Considering the running time of the binary search algorithm as presented, we observed that the constant number of primitive operations are executed at each recursive call of the method of a binary search. Right, so we determined that we create that the binary search was log n time, right? We split off by a factor of a factor of 1/2 every recursion through the program, right? Via this midpoint selection here. So hence the running time is proportional to the number of recursion calls performed. We will show that at most the log n plus 1 recursive calls are made during a binary search of a sequence having n elements leading to the following claim. We'll have at most log n plus 1 recursive calls are made during a binary search for a sequence having n elements leading the following claim. The binary search algorithm runs in O log n time for a sorted sequence with n elements. That's our prop. And then our justification is going to say, to prove this claim, oh, I think I just spat. Whoops, sorry guys. That's what happens when you're reading out aloud for 2.5 hours. You tend to lose some stuff. Okay, so to prove this claim, a crucial fact is that with each recursive call to the number of candidate entries still has to be searched is given by, to prove this claim, a crucial fact is that with each recursive call, the number of candidate entries still has to be searched is given by the value of high minus low plus 1. So to prove, a crucial fact is that with each recursive call, the number of candidate entries still to be searched is given by the value high minus low plus 1. So if our low is 0, our high is 10, 11, we have to search 11 entries. So if our list still have to be searched is given by the value. So why would you have to do one more entry than the high minus the low? So let's say the low is for indexings, right? So if you have a value, if you have a list of 10 up with a length of 10, meaning that the high minus the low would be 10, plus 1 would be 11. So what is the 11 justifying? Hey Pavan, thanks so much for joining. I appreciate you leaving a comment and joining me this evening, learning some DSA. How are you doing today? Perform binary search to find I in above string. Because even in odd positions. Moreover, the number of remaining candidates is reduced by at least 1/2 with each recursive call. So if you have a list with the length of 10, why is the number of candidates to be searched 11? The number of remaining candidates is reduced by at least 1/2 with each recursive call. Specifically, from the definition of mid, the number of remaining candidates is either mid minus 1 minus low plus 1 equals the floor of low plus high divided by 2 minus low is less than or equal to high minus low plus 1 over 2. Okay. Initially, the number of candidates is n. After the first call in the binary search, it is at most n minus 2. After the second call, it's most n minus 4, and so on. In general, after the jth call in the binary search, the number of candidate entries remaining is at most n divided by 2 to the power of j. In the worst case, an unsuccessful search, the recursion call stops when there are no reported more candidate entries. Hence, the maximum number of recursion calls performed is the smallest integer r such that n over 2 to the power of r is less than 1. In other words, recalling that we omit a logarithm's base when it is 2, r is greater than log n, thus we have r is equal to the floor of log n plus 1, which implies that a binary search runs in O log n time. So we were just proving with this that it ran in O log n time. But that still doesn't answer my question about if you have a 0 plus 11 divided by 2, it's 5.5. Yeah, okay. So you take the floor, though, for the midpoint. Oh, but you round up? No, but if you add 1, that would just be 6.5. Oh no, but you're divided by 2 actually. So no, hold on. Let me just see. Let's ask the almighty orb here. When in doubt, right? Um, y is with the initial call to a binary search the number of candidates to search through is 1 larger than n. The number of candidates in a binary search being high-low is direct consequence of how we index and define the search of the range within an array or list. Zero based in most programs, okay, we zero based, got you. So the low high we n minus 1. So to compute the number of candidates in the range from low to high, you count the difference between the indices and add 1. The plus 1 ensures that both the starting index low and the index high are included in the count. Initial number of candidates. When you start with the binary search is a low of 0, high is n minus 1. Substituting this into the formula, n minus 1 minus 0 plus 1 is equal to n. Hence, the number of candidates to search through is exactly n, not n plus 1. Oh, gotcha, yeah. If you think there are n plus 1 candidates initially, it might stem from misunderstanding the zero-based indexing or misapplying the formula. The plus 1 accounts for the inclusion of both endpoints, but does not add an extra candidate beyond the actual number of elements of the array. Okay, so it just had to account for the starting and endpoints. Because if you have a list with a length of 5, you get index values of 0, 1, 2, 3, and 4. So high would be 0. Oh, these are indexes. So if you have a... It's interesting. Okay, let's move on here to computing. Let's let that marinate. Let's let that sit with us for a little bit. Let's let that, as they would say, maybe hold some space. Didn't think you'd get that one from me tonight, did you? Did not think you'd get that one from me. Okay, let's compute disk space usage. Our final recursive algorithm for section 4.1 was that for computing the overall disk space for a specified portion of a file system. To start, the problem size for analysis, we let n denote the number of the file system entries in the portion of the file systems that is considered. For example, the system portrayed in figure 4.6 has n equals 19 entries. 4.6 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 entries. Okay, just nodes in our tree, pretty much. To characterize the cumulative time spent for an initial call to the disk usage function, we must analyze the total number of recursive invocations that are made, as well as the number of operations that are executed within those invocations. To characterize the cumulative time spent for initial call to the disk usage function, we must analyze the total number of recursive invocations that are made, okay? As well as the number of operations that are executed within those. Okay, gotcha. We begin by showing that there are precisely n recursive invocations of the function. In particular, 1 for each entry of the relevant portion of the file system. Intuitively, this is because a call to disk usage for a particular entry E of the file system is only made from within the for loop of code fragment 4.15. So here's code fragment 4.15. We have a for loop within here. Gotcha. Did I copy that over here already? No, I need to put that in here for file systems. Oop, hold on. Explored once. Okay. To formalize this argument, we can define the nesting level of each entry such that the entry on which we began has nesting level 0. To formalize this argument, we can define the nesting level of each entry as that the entry of having which we begin has nesting level 0. Entries stored directly within it have nesting level 1. Entries stored within those two, got you. We can prove by induction that there is exactly one recursive invocation of disk usage upon each entry at nest level k. As a base case, when k is equal to 0, the only recursive invocation made is at the initial one. As the inductive step, once we know that there's exactly one recursive invocation for each entry at nesting level k, we can claim that there is exactly one invocation for each entry e at nesting level k, made within the for loop for each entry at level k that contains e. That made absolutely zero sense. Please break this down for me. Sure, let's break this down. Nesting level. So we have the level of the entry in hierarchy. Level 0, the starting entries. 1 is entries directly contained within level 0. Level 2 is entries inside those level 1 entries, and so on. Recursive invocation. The function call itself for each entry occurs. The goal is to prove by induction okay. Having established that there is one recursive call for each entry of the file system, we return to the question of the overall computation time for the algorithm. It would be great if we could argue that we spend O of 1 time in any single invocation of the function, but that is just not the case. While there are a constant number of steps reflect in the call to what kind of sentence is this? While there are a constant number of steps reflect in the call to I think we're missing a comma here. Reflect in the call to os.path.getSize to compute this disk usage directly at that entry. When the entry is a directory, the body of the usage function includes a for loop that iterates over all entries that are contained within the directory. In the worst case, it is possible that one entry includes n-1 others. Based on this reasoning, we could conclude that there are O of n recursive calls, each of which runs an O of n time, leading to an overall running time of O of n squared. While this upper bound is technically true, it is not a tight upper bound. Remarkably, we can prove the stronger bound that a recursive algorithm for disk underscore usage completes in O of n time. The weaker bound was pessimistic because it assumed a worst case number of entries for each directory. While it is possible that some directories contain a number of entries proportional to n, they cannot all contain that many. To prove the stronger claim, we choose to consider the overall number of iterations of the for loop across all recursive calls. We claim there are precisely n-1 such iteration of that loop overall. We base this claim on the fact that each iteration of that loop makes a recursive call to disk usage, and yet we have already concluded there are a total of n calls to disk usage, including the original call. We therefore conclude that there are O of n recursive calls, each with use of O of 1 time outside the loop, and that the overall number of operations due to the loop is O of n. Summing all of these bounds, the number of operations is O of n. The argument we have made is more advanced than the earlier examples of recursion. The idea that we can sometimes have a tighter bound on a series of operations by considering the cumulative effect rather than assuming that each achieves the worst case is technically called amortization. We will see a further example of such an analysis in section 5.3. Furthermore, a file system is an implicit example of a data structure known as a tree. And our disk usage algorithm is really a manifestation of a more general algorithm known as a tree traversal. Trees will be the focus of Chapter 8, and the argument about O of n running time of the disk usage algorithm will be generalized for the tree traversals in Section 8.4. Wow, lots of words there, guys. We read a lot of stuff there, but we hopefully are getting it. Here, my hair is all crazy. I look like a blockhead. All right. Okay, so what I gathered from this is that we have, as we traverse through these trees, we are assuming like the worst running time at each recursion step, and that is having like an overall pessimistic viewpoint apparently. So you can, that would have like a weaker bound, right? Meaning like that if every instance of the recursion has the worst case running time, then that would have a weaker bound. So we can have a tighter upper bound more closely, or like a tighter upper bound. We can prove a stronger bound that the recursive algorithm for disk usage completes in O of n time. So the weaker bound was a pessimistic because it assumed the worst case number of entries for each directory, meaning that it had, so let's go back up to where it determined. Having established that there is one recursive call for each entry of the file system, we return to the question of the overall computation. It would be great if we could argue that we spend O of 1 time in any single invocation of the function, but that's not the case. While there are a constant number of steps reflect in the call to os.getSize to compute directly that the entry, when the entry is not a directory, the body of the disk usage function includes a for loop that iterates over all entries that are contained in the directory. In the worst case, it is possible that one entry includes n minus 1 others. Okay. Based on this reasoning, we can conclude that there are O of n recursive calls, each of which run in O of n time, leading to overall n squared. But that's a pessimistic viewpoint, and we can think about this in the argument we have made is more advanced than the earlier examples of recursion. The idea that we can sometimes get a tighter bound on a series of operations by considering the cumulative effect, rather than assuming that each achieves the worst case, is a technique called amortization. So I'm sure when we get into these further chapters, we're going to learn a lot more about these specific, examples. Vance, thanks so much for coming in and saying what's up. Yeah, congrats on 400. No, congrats to you guys. Again, you guys are the ones that are supporting me here. I can't do it here without the support to get to that number. So thank you guys so much for that. Okay. 4.3 recursion run amok. Okay, let's go ahead, and I think this is a good place to pause our learning so far for DSA. Let's go ahead and pull up the. Let me go. I need to push this. Let me take this guy. I'll say git add, git commit. Again, guys, if you want access to all these answers and these notes, they're on my GitHub right now, linked below. Feel free to grab them from there. Continued with chapter 4 learning notes. Push this. Cool. Let's close out of this guy, and then let's open up our small business manager. Now give me 1 second. I'm just going to pop on my heater. It's starting to get pretty cold, so you might hear a slight hum in the background. Thanks for your patience, guys. I got my heater on. It's starting to get chilly in here. It's like a storm outside. Ooh, brr. Okay. I want to work on this for a little bit tonight, but I will be. Trust me, guys. This weekend, when I have more time, I work a 9 to 5 as a chemist throughout the week. So, again, when I have more time this weekend, we're gonna be streaming a lot this weekend, maybe multiple times a day. So I'm gonna be getting a lot of work done on the project this weekend. A heavy focus on the project this weekend. Thank you, Angela, for stopping in. I appreciate it. I'll see you some other time. Thank you. It's a pleasure, as always, to hear from you. Okay, so right now we have our system here, and we need to add in implementation for these two functions here. We initially are allowing the user to search for an item number. We run the find by item number function. We print an error if not found, and then we print the found item from here. So we could probably find by item number. So this search that's going on is just like what we learned, right? So find by item number, we're doing a search through all items in this list, and we're returning them. So this is going to be a sequential algorithm for these three if statements here. So this will run in a linear time proportional. So we can make this run in O log n time if we wanted to, right? We could make this run in O log n time. We could say we have number so we could say we need to have a number. We have a target for number. We have a so let me go ahead. What if I'm going to go ahead and just make a dummy function here called def find item by number. I'm going to take in, we're going to take in a number or a target number. We're going to, or just target target, we'll say this is going to be high, and then we're going to say low. Right, that's what that algorithm used, correct? Low, high. So what we're going to do is if we wanted to implement this, we would have if low becomes greater than high, we want to return none, right? Else, we will say low is equal to if low is equal to is going to be the all items we'll say so we'll first check items. We'll then check for sale items. And then we will then check sold items, right? And so low is going to equal to zero, actually, right? Low is going to equal to zero. All item, and then the high is going to equal to the all items Ahmed Jalan, thanks so much for coming in and joining me. He says, "Have you ever had a programming job? What language are you most proficient in?" I've never had a programming job, but I work as a chemist. I have a degree in human biology and a minor in chemistry. I graduated back in 2021. I work as a formulation chemist, and I currently am just studying heavily into Python. I want to gain a mastery in this really before I move on to other subjects because I don't want to leave any gaps in my general knowledge, and I don't want to move on from a topic before I've really solidified it and mastered it. So through that, I wanted to really focus on a single language for the start and develop a high level of efficiency and proficiency in it before considering other things. So thanks so much for leaving a comment though and joining along. I appreciate you. Okay, so the high is equal to in the book they say the high is equal to no, you provide a high. Mm. So we need to provide a high value, which high is going to be the length I'm trying to figure out how to access all three of these lists. All items. Okay, so we'll say, how about this? Let's go length. That'll give me the length of all three of these values summed, right? Hopefully. So what if I just did this plus like this, rather. Right? And then I'll do it one more time. But for sold items, so this will give me the high will be the total length of the entire all items dictionary values lists returned, right? And so then if we have that, um, we will else, right? We establish a low We say if we need to establish this mid now, right? So we would say mid is equal to our low, no, our low plus our high divided by 2, or is it minus? Plus our high divided by 2, yeah. Finding the average. Two. We then say if target is less than mid, we will so if the target is less than not mid but the range of low to high at an index value of mid, then we will so this is going to give us a range of 0 all the way to the top of our list. We need to include this high value, right? So you say +1 here to include the high value. The highest most value in the list, so we need to do that. So this is a 0 to, how would it be, like, if we have 3, 3, and 3, that'd be 9. So 0 to 9 would be 0 all the way to 8, so we need to include 9. Yeah, so high +1, exactly. High is an index. So the highest it wouldn't be high +1 actually. Because if the low is 0, let's say we have 3 items in each list. So the lengths would be 3, 3, and 3, providing a total 9 for the high. We go 0 plus 9 divided by 2 would give us a value of what? 4.5? We'd floor that value, so we'd get 4. So if, let's say we have 3, if target is less than no, not at our, not this. We want to do all items dot values mid. So the thing that's interesting, I have 3 separate lists. So I take the low, and my high is the length of all 3 lists combined. So this would give me a midpoint. If we have, let's say we have a total of 10 items. So this would be give me a midpoint of 5, right? Low plus high. A middle index of 0 plus 10 10 divided by 2 would be 5. Middle index of 5. Should be 0 all the way to 9, so the 5 would be the middle, right? Because we have 6, 7, 8, 9, and then 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7. For those of you that are watching, I'm trying to convert this sequential search function that we wrote into a binary search function. So I have a low of 0 and I have a high of length of all the three of my lists, right? Now, I could do the binary search across each list individually. That wouldn't be too hard, but then that would be having a binary search, a log n plus a log n plus a log n, which would just be log n time. So it still would remain with the log n efficiency if I did 3 individual binary searches for the item. But I'm trying to do this if I want. What does all items.values return me if I have all? Will it return me a list of lists? What will, I'm going to yell at you. What will dot values return when all values in the dict are lists? If all values in the dictionaries are lists, calling.all will return a view object containing the list, not their contents directly. This object can be iterated over, and each item will be one of the lists. So it'll give me a list of lists. You need to use individual lists. You can convert into a list or iterate over it directly. My dict becomes a list. So it will return a list of lists. Yes, if all values in the dictionary are lists, calling.values will effectively return a view object containing a list of lists. However, it is important to note that the result itself is not a list. It is a dict values object when it is iterable, which is iterable and can behave like a list in many contexts. If you explicitly convert it to a list using lists, it will become a list of lists. So then what if I wanted to truncate, I spell truncate it to one list? You want to flatten the list and combine lists of lists and combine lists into single. You can use several methods. You can use itertools.chain, flatten list for a list 4 item and sublist.dictionary 4 item. No, I don't want to. That'll give me an increased time complexity of O of n if I do that. What does the indexing look like for a list of lists? In a list of lists, indexing works similarly to how it works for regular lists. Okay, so then I think we can do that actually. Okay, so then let's take this. We'll convert this to a list. We'll apply dot value mid. No, I don't want to. So this will give me the mid index. Okay, so I think this will return me a dict object, which will be all the values which can be iterated over. So we'll get the mid value of that dict object representation. If the target is less than, so we have this right, I think. If it's less than, we're going to call find item number again, and we're going to provide a target. We're going to provide a low of low is equal to 0. And the high is going to equal to the mid minus 1. Yeah. So then, if target is greater than all items dot values at that mid index, we will recur by find item number again. We will take in the target value. We will take a low of equal to mid plus 1, and then our high is going to remain as high. Okay. No, it's going to be, I need a 0 here, because that might get overwritten here. So 0, plus 1 all the way to high. The high will be, do they say high, or do they say, yeah, they do say high. And it's equal to low. Low, high is equal to high. Okay. So we're going to then return SS low, you make a good point. My lists are not sorted yet. So we will leave, I will comment out this function until we have implemented a sorting for our items. Right. Yeah, we need to implement a sorting. Thank you for reminding me. So this is not going to work appropriately unless we have a sorted list. So then what we're going to do is return these right here. So I think I think this is our program. This is our function. So we had a find item function earlier, right, you guys, that iterated through the lists. Wait, so let me back up. The all the items are being stored in a dictionary where the keys are a definition for the type of item, for just items, for sale item or sold item. And then the values are a list of all of those items, right? Under those certain category keys. So in this function, we run O of n time plus O of n time plus O of n. No. In the worst case scenario, we have items in every single list, so we run in this in O of n plus O of n plus O of n for a total of linear time for every item in our list, right? That's what this function does. This runs in linear time. This function here will run in log n time because we are having our list on each recursion of the find by item number function. So right, return low mid minus 1, high equals high low. Interesting. Amid Jalan says, which state are you in? I'm in California. I'm in the Bay Area. Okay, so, but this will not work unless we have our items in a sorted list. Now, they are currently sorted right now, right? So, I bet you this function will work. So my question is though, if target, we're missing this. Wait, what's going on here? I think I'm missing some stuff here. So if low is greater than high, we return none. Low is equal to 0, else we make the mid. Okay, we take this up here. This goes here, else we take the mid, and when we say if target is equal to all items at the midpoint, then we will return true. So this is just going to return that value. Why? See you, Jordan Woods. Thanks so much for stopping in this evening. I appreciate you so much. Thanks so much for coming in. I'll see you tomorrow. So I don't want to return a target. Find by number. We would return the item number. I want to return the object with that target value. So if I put in search by item number, ah, so I think we're missing something crucial. So if we're finding by item number using the target, the target's an item number. So this is going to be dot mid. So what if we say find item by, and then we give a type argument here with a default of 0, of none. So we say find item by type, item number. Yeah, I've learned about some type annotations and stuff, but I I oftentimes forget to put them in. I have a couple of things here and stuff, but I'm kind of lazy. Sorry. I definitely need to get better at that. So we can have a type provided. If we want to do type is equal to default empty string. If type equal to so we're going to make a types. No. Equal to quote item number. We're going to so if type is equal to item number, we're going to so if type actually, if they provide a type, we're going to run the recursion function. So if type, we're going to get into this function. So if they provide a type, yeah, okay, if they provide a type, well, is an empty string will an empty string return a true bool? No, an empty string will return false. Okay. So if type, we will run dot, and then we will say mid divided by 2 if target is equal to all items at that midpoint. all item dot keys at that midpoint. No, sorry, all item dot values. If target is equal to all items dot values at that midpoint, we return at that midpoint dot type, like that. So this is going to return it's going to access, sorry, what this is doing, guys, is it's going to go into the all items dictionary. It's going to pull all the values, which are going to be a list of lists. It's going to then select the midpoint from that list of lists. And then it's going to apply and check if the dot type provided, so for item number, is equal to the target, which would be the item number. Then we return the all items dot values at that midpoint, just like that. What do you guys think about that? How do we feel about this? So what's happening here is the user can provide a type. If they provide a type, we go into the find, right? Else raise value error type equal to a list of item number item number. No, so we need to say if type equal to quote item number, we're going to do this. Else we don't need to do anything else. So if it's equal to item number, we're going to run we're going to do a binary search for the find by item by item number. So I'm going to move because it's a default, it has to be at the end actually. I like this. So if the user provides type equals item number, then we're going to run a binary search for all of the value. We're going to run a binary search for that item number. Our low is going to be 0 and our high is going to be the length of all three of our lists combined together. And then, or we'll say length of all items, rather, dot values like that. So dot value dict dot values time complexity, and O of n, where n is the number of value pairs. So if we use the values function here or method, we are going to be an O of n type. Right. So that being said, if I were to use the dict.values as my data structure for my algorithm, that is in binary search, it would increase my growth rate to O of n. Yes. Damn it! Oh, that sucks. That sucks. Using dict values will directly in your algorithm for binary search would likely increase the time complexity of n, but for a different reason than you might expect. Let's break it down. Binary search assumption. Binary search operates on a sorted collection and requires accessing the elements via indices, which is efficient in data structures like lists or arrays where you can directly access elements by position in O of 1 time. Dictionary values. When you use dict.values, it returns a view object that allows you to access values in the dictionary, but does not support indexing, which is required for binary search. To use binary search, you would need to first convert the values into a list. Converting the dictionary to a list would take O of n time. So I can't access the midpoint like this. I can't index into values. I'd have to list this like so. And that would make me cause to be an O of n time. Oh, that sucks. So then what can I do? SSLowRL says, does that mean you need to keep a specific list for each type you want to sort by? A specific list for each type I want to sort by. Yeah, I guess you would, or you would just have to override the current list with that filter. Ah, this is interesting. Dang it. So I could say I'm going to have to do a binary search across all three and just be an O log n times with a constant of 3 out front. It'll slow me down slightly, but not terribly. Okay. All right, let's try that. So if they give an item number, we're going to do a binary search. We're going to do a binary search. Low. Do they establish the low and the high here? No, they don't. So I need to take this guy, put it up here. Right, so we'll have to take this, add it, items, and we'll take this, add it, oops, sold items, so no, we'll take this out, we'll take this guy, take it away if it's here, like that, paste that there. But if every time this is called, it'll set this rather than filling in these. Hey Gina, I'll call you in a second. Hold on. So if I set these like this, it will actually, yeah, that won't work. I can't set these in the function in itself. So I need to provide a low and a provide a high starting point. So if type is equal to item number, and if low is greater than the high, we return none. Else, we get the mid value from the low and the high. If the target is equal to all items, so we'll take this, we'll do all items. We'll access the items. We'll get to the midpoint and we'll get the type, dot type. Return quote items, right? So that we'll return the mid value. No, I looked that up, SSO. That was my question before. Is calling values will run in O of n time. So this will slow my algorithm down to O of n time rather than being in O of log n time. It'll ruin it. So I'm getting rid of the values and just accessing the list itself on an individual basis. So I'm going to have to run this in 3 log n time, where I'll have 3 individual searches that happen in binary, one after the other. So it'll be 3 log n. That's just how it's going to be, I guess. So if target whoops. What's going on here? This is going to be list right, so like that. So we would return, if it's the target, the item number in this case is equal to the dictionary items list midpoint value So if this is 7, it'll access the 7th item in the all items dictionary list. Sorry, and then the item number from the type here. Return all items admitted, else we'll do these. Okay. So then we'll copy all of this over, or copy this down. So if type is equal to no, sorry. So if I set out here, if I predetermine the high variable to be the length of all three types together, list types together, then every time I recurse, high will then be overridden by that value, and I can't have that. So that's why I can't set that initially. So the high is going to have to be set here as all three lists together initially. Yeah. So if they provide a type item number, now what if I say dict quote list 1 quote list 2 quote list 3. If you are referring to a dictionary with multiple keys, such as it seems you're trying to use a tuple or a list as a key, here's some clarification on how it works. Dictionary key structure. In Python, dictionaries allow immutable data types like strings, numbers, and tuples and to be used as keys. However, like lists, however, are immutable and cannot be used as dictionary keys. If you're trying to make the values associated with the keys are lists. If your values associated with the keys in your dictionary list and you're looking to perform a binary search on the contents of the list, here's a breakdown of how you can approach it. If you want to perform a binary search on the contents of the list in the dictionary, your list must be sorted. Extracting the list, you would access the list for a given key in the dictionary and perform a binary search on that list. SSLow says it's only O of n. It's O of n only if you're iterating through all the elements and values, right? But aren't you just using an index? Exactly. So that's the problem. SSLow is that I didn't know, and this is new to me as well. So we're learning this together. Is that when you use the hiccups, when you use the dot value method applied to dictionaries, or sorry, the dot values method applied to dictionaries, or dict dot values, it returns a dict object which behaves similarly to lists but cannot be indexed into. It can be iterated over, but it cannot be indexed into. So because it doesn't behave exactly as a list, so you would have to convert that dict object into a list itself, and that would cause the O of n time complexity. Because then it would iterate through all the values in that, transferring each one into a list for every n value in the dict object, right? unfortunately. That's how that would work. Yeah, I didn't know that either. It return is a dict object rather than a list. It behaves similarly. It can be iterated over, but it cannot be indexed into. So when I was doing all items dot values with a mid, that would actually throw me an index error because it could not index into that dict object. But this will be able to because my the value associated to the quote item key is a list just by the nature of my program. So now how would we do the search if else? So then how could I duplicate this code to? No, it would have to. This is tough because I would have to run a search on each list individually. But by doing that, I'd have to call the function 3 times. Um, I think I'm going to pause here for this evening, you guys. We're past 10:30 tonight. I appreciate you guys joining me. I'm gonna get some rest. I was up late until like 1 or 30 a.m. last night working on the Discord for everybody, getting like some more features for the Odin project added in, getting some like just kind of spicing it up with some general styling and stuff. But tomorrow, guys, I will be coming live tomorrow morning. I'm going to do a morning stream to help capture some of our East Coast uh, needs to capture some of our East Coast and our international subs. We know that a lot of them go to bed or are in the early AMs of the stream when we're in the PMs here. So um, Rice for 88 says, "Bro needs a hash set." If that would help me in this circumstance, I do because I am trying to implement a binary search here over a list that's a dictionary. But the thing is I a list that's housed inside of a dictionary as a value. But the thing is I need to perform this 3 times across different keys. And I can't because I have to put in a single high value. So what if I did this? What if I provided a high for what if I made now this could get complex, but what if I gave the user the opportunity to provide a low for a low and then they can provide 3 separate highs, which would all correspond to the length of the item number list. So what if I did high of items? We did high of for sale items, and we did the high of the sold items, and we set these equal to the length of all items sold items. We make this guy equal to the length of all items for sale items, and we make this guy equal to the length of all items items, right? So if we did that, we could then say if item number is less than or equal to, is greater than high underscore items, or so this what this would do a problem that would arise with this way of going about it is if they have different number of items in each list, then they would recur at different rates, causing one to be thrown a none what if I added it to a what if I did this? Found item equals none. What if I make actually found item an empty list? Not return none, but we say if it's high, we'd pass. We wouldn't do anything else. If it's low, we would say we would do this high underscore items. We would take high equals high underscore items here. So then we would found item found is equal to this. And then we're going to found item dot append the item found. So what's going on here is if we get an item number and we, instead of returning none, we're just going to pass and say, okay, we didn't find any, and not actually go through our binary search. If we do find an item, we're going to actually append that item to our found item list, and at the end of this function, we're going to return found item. We're going to return a list object. So this should only find one item. So we're going to return the first index value of found item. either return a value or return none. So if found item, we will return this. Oop. Else return none. Right? So we have an item number tag type. We do the check to obviously stop our recursion if the low becomes higher than the high for the items. Else, we're going to find the midpoint between our low and our high items. We're going to say mid items, mid items, mid items, mid items, mid items, mid items, right? Mid items. So then what we're going to do is we're going to say the mid for sale items is going to equal to low of low plus the high of the for sale items. We're going to then say we're going to copy this down and say if target is equal to all items for sale items mid for sale items dot type item found is equal to all item for sale items mid for sale items, and we're going to append that found item. So then, if target, we need to do the recursion steps here. We're going to copy these. I'll copy this one over first. If target all items for sale items mid items for sale items return find item target low equals low for sale items -1, and then we'll copy this one down and say if this should say for sale items mid for sale items. I'll just copy this here and go like there. Mid for sale items, high for sale items. Right? So that'll run that binary search for those. So then we need to do this one more time for the sold items as well. Sold items, mid for sold items. So we need to add a mid for sold items here. High sold items. So then where were we? Sold items, mid sold items, find item low, target mid sold items -1, and then we're going to need to copy this one down one more and say sold items, mid sold items, find item by mid sold items +1 high for sold items. Okay, so we should have a mid items now. We have a mid items for our midpoint for the items. We have a midpoint for the for sale items, and we have a midpoint for the sold items. We use the high of items, the high of for sold items, and the high of sold items. We then say if target is equal to all items, and we also need to add one here, and say if target is equal to all items, sold items, mid sold items dot type item found equals all item sold items mid sold items. We're going to append the item found. We're going to say elif here, I think. Right, and then this is going to be elif if we want to do these evaluations, all of them, and we only want to append a single item that's found, so it's only going to do one of these. Cool. So then, all right, now I know we wrote a lot there, guys, but what I wrote was I now allow the user to provide a high items length, a high items, a high for sold items, and a high for the sold items. So because we have our items separated into 3 lists, each of those lists are represent that category. We need to run a binary search across all 3 of them and return the single item that's found. So what I did was I created an empty list, which is a found item. We obviously have that type for item number. So if they provide an item number type, we're going to run a binary search. If we run a another type of type or a different, like by date, we're going to do a different type of search. But yeah, so this is just for sorted arrays and stuff. So if the low, right, if the low becomes greater than the high for items, we're going to pass, or low is greater than high if low I think I just wasted a lot of time here because now I'm seeing if the low is greater than the high items, we're passing for that specific. But if we say or okay, if we say or only one has to be met for it to move on and do this. So it will try to do this if one of these passes. So we'll say if low we're going to pass, we need a different conditional and say if low greater than high for sale items, then we're going to pass, and if low is greater than high for the sold items, we're going to pass. Else, we're going to do a search across all three of those lists using the high for items, the high for sale, and the high for sold as our first occurrence, and then cool. I want to see. I think that this is so. It's for sale, sold, sold, items, mid items, items, mid items, items found. For sale, for sale, for sale, mid for sale, item found, append, sold items, sold items, sold items, sold items. Okay, those are matching. So if items, mid items, for sale items, mid for sale items, sold items, mid for sold items, those are all matching. Items, mid items, for sale items, mid for sale items, those are matching. Sold items, mid for sold items. We have high for sold items, high for sale items, and then high items here. Yeah, I think this looks pretty good. So like we said is we're just doing a triple binary search across three different lists within this function. So let me go ahead and take this, copy. Here is my attempt at a triple binary search across three separate lists, looking for a single value amongst all three. All right, let's see what that says. Okay, let's see what it says. Your attempt at a triple binary search across three lists has the right idea, but there are a few areas that could be refined for clarity, efficiency, and correctness. Key issues: nested binary search logic. You're trying to perform binary search across three different lists in parallel. However, your logic doesn't always return the right bounds when comparing elements across the three lists. Recursion on wrong functions. You're calling find by item by number. Oh, that's, yeah. So we need to call find by, and then we need to give it these other. Oh, okay, so we have some functions that we need to clean up because we have some because we changed these definitions here. Gotcha. So we're calling find by, we need to call by the correct function here because we changed the name. Find by, and find by. Low is equal to that. High underscore sold items is equal to high sold items. High sold items. High items. High. Oh no, whoops. High. For full ends for sale items. High items. High sold items is equal to high for sale items is equal to, and high items is equal to. Okay, then we have if I type high items, okay, so I think that fixed that. So let's see what it says now. Okay, I fixed some stuff. It looks like you've made some changes, but there's still a few issues. Recursive calls. You're calling find by item number in the first if block. Okay, get rid of that. Incorrect range for recursion. If your recursive call is using the low instead of adjusting it based on the current mid value for the different lists, when searching for the list, the low and high value should be adjusted based on the target comparison specified to the respective lists. So low, low, low. These are all the same. These ones are the same except for just the changes. So then, what's the problem here? Sold item, for sale item, items, mid items, high items, high for sale items, high sold items, low, low, low. And then we take in our low is equal to our high sold items is for our high. So if I take this now, put it in, what does it say? Your approach has the right structure, but there's still some issues that need fixing. Ensure it works as expected. So recursive calls, you're performing a recursive call for each of the three lists, but your logic to adjust the low and high values to handle each. While low is less than or equal to sold, high. So instead of doing passes, they run while loops. And you get the low. If target is equal to the type. Hmm. Interesting. We're on the right track. We're definitely getting there, but I am gonna wrap it up for today. It's 11 o'clock. I've not got much sleep in the past 24 hours. My brain is pretty cooked, but I'm going to rest up here, guys, and I'll see you tomorrow bright and early, probably around 9 or 10 p.m. PST. Um, I'll stream for maybe about uh, I'll probably hop on around 9 PST, and I'll stream for about 3 or 4 hours. And then I will head out. I have an event I have to head out to in the afternoon. And then I will probably be back and do another late stream around maybe 8 or 9 p.m. tomorrow. Um, and then on Sunday, I'm gonna do probably a double header stream, probably an early morning one, take a lunch break, and then come back after lunch and do another stream after that. So we're gonna get a lot done. Again, I know I was working on this, but you guys, we just spent an hour of our time, an hour and a half almost, actually trying to implement a binary search that we just learned about into our program. So we're getting hands-on practice with these concepts from the book, and we're trying to apply them. That's all you can ask for when learning something, is you attempt to apply it into something that will drastically increase your retention, your ability to future implement it into things. So just by, we were able to, we weren't successful in this attempt. Well, obviously we'll try again tomorrow, but um, yeah, we will write a binary search here, and we will be successful in this. And so I'm feeling really good. It's just one after the other. This is a great starting place for us to be at. We thought about this function in a lot of different ways. You saw me probably just sitting here looking at it, reading it over and over again, thinking about. I'm not thinking about the bugs really. I'm thinking about it from a user's point of view. Like I'm trying to think about, like, I'm going through iterations of it in my head. Oh, if I plugged in this, what would happen? I'm kind of going through the code in my mind with different scenarios in mind, and how it would be handled. So that's kind of my approach to programming. I take a very user, like a third party user point of view, from someone, like as if they've never seen the code before, and so that's often, or used it before. So that's kind of how I go about conveying these, putting the pen to paper basically, or the mouse to IDE. Anyways, um, I really appreciate you guys joining me on this Friday evening. It's not an easy task to give up, a couple hours out of your time on a Friday, to spend dedicated to learning. So give yourself a pat on the back and a round of applause. Right? It's huge uh, gain for you. You studied today. It should be a big win on a Friday of all days, where other people are out partying, having fun. Bit good to them, but we're here studying, improving ourselves academically, and just developing hobbies. So or developing skills, sorry, rather. But anyways, I'm done rambling for now. I'll talk to you guys later. I'm stuttering, and it's time to end the stream. I've been going for 4 hours. So I'll actually just hold off for another 45 seconds to hit the 4 hour mark, because I like a nice even number, and then I'll see you guys tomorrow. I can't wait to talk to you guys again tomorrow, but 30 seconds here and we'll bow out. So if you have any last minute chats, feel free to ping them. Again, guys, I am a chemist. I have a degree in human biology and minor in chemistry, where I work as a formulation chemist in the Bay Area, California. I am learning programming on the side to develop new skills, teach myself new things, prove that I can do hard things, maybe even transition into the field one day. I make a lot of projects, and I have a Discord link below with all of my study resources in one area provided to you guys for free. So feel free to join the Discord, and I'll see you guys tomorrow.